Hey everyone, and welcome back to the Answer Robotics channel. And now for the past few videos, we've been deep in the trenches architecturing our high-performance LLM runtime from the grounds up in pure C. And we're focused on heavily building on the solid foundations, getting that single contiguous memory layout perfect, ensuring cache and a huge page alignment, and designing our token parallel framework and the GEMM, which is the general matrix multiplication kernels. And especially for CPU execution using HPC concepts. But today we're going to be building on that foundation by diving into one of the most important and you can almost say revolutionary components of the modern transformer, which is the layer normalization. Now, this isn't just a talk about, a single formula. We're going to cover the complete story. We'll start with the core mathematical problem it solves, sees the simple architecture change that enabled models like GPT-2 to scale to incredible depths, and more importantly, connect it all back to our project by looking at how to implement with maximum performance using HPC concepts, single instruction multiple data, and just like what we're doing in our C code. So let's get on with our presentation. Now, the fundamental challenge is that neural networks work best when inputs have stable statistical properties. But deep networks naturally create chaos. As we go deeper, the activation shifts and explodes unpredictably. Now, this chart shows the problem. So let's have a little deeper look at this. Now, when you look at this chart, by layer 10 or 20, the distribution becomes completely unimaginable. And this is the internal covariance shift. The core problem LayerNorm solves. So what we're trying to show is that once you start to increase the number of layers, there is a problem in which how the training actually works. And based on this is what we're trying to solve. And without the stable input, each layer spends all its time adapting to chaos instead of learning meaningful patterns. So that's the kind of the idea of where the whole concept of LayerNorm came in the first place. So now let's make this concrete. When we say high variance, we mean unpredictable, chaotic signals that make learning impossible. So look at these training symptoms. Loss curves that spike randomly, gradients that explode or vanish, activations going to extreme values. The analogy is perfect. It's like trying to learn to paint when someone keeps changing your canvas, paint colors and brushes mid-stroke. So LayerNorm gives us a stable, predictable canvas we need. So here we're trying to look at this. This is what we're trying to expect, the low variance. But if you do not have LayerNorm, you could, basically have a training with high variance, which is bad, especially when you increase the number of layers. So this is basically when you're training normal neural networks, this is what would really happen. So what does LayerNorm actually do? Let's give a better analogy. Now think of each layer as a photo editor working on an image. Now, high variance means chaotic, flickering inputs, impossible to work with because we don't know what the input might look like. There might be a little bit of spelling mistakes in this case, or it could be a spelling of a different language, whatever be it. So that your input could be really chaotic, and in an image it could be with low light or with highlight. So we want to kind of normalize it. So LayerNorm is like giving each editor a clean, neutral canvas first, and you can watch this photo progression. The raw chaotic input. And then we go through LayerNorm, it normalizes it, and it cleans it up, and then we standardize the output ready for the next layer. So every layer gets consistent workable inputs instead of fighting unpredictable chaos. This is the core insight that makes deep learning possible. So what we're trying to do is take this input and kind of make it more normal so that we can now have a more stable learning, especially when you go into deeper and deeper layers. That's what LayerNorm is actually doing from a mathematical standpoint. So where exactly is LayerNorm applied? In a layer, LayerNorm appears twice in every transformer layer. Let's trace the complete computation flow. Input goes to LayerNorm, so this is one layer, and this is GPT-2 structure. But even in 2025 and onwards, the structures are very, very similar. Today instead of LayerNorm, you use RMS norm instead of multi-head attention. You use a different type of algorithm, but they're all subtle changes. But the main core concept and the structure is all very, very relevant, even though this is pretty much the GPT-2 architecture. So before the multi-head attention, we have the LayerNorm. So we're kind of normalizing it right at the input of this layer. And then the LayerNorm before the feed-forward neural network. So it's applied twice. So when the output of the multi-head attention again goes to the feed-forward network through FFN, And then you have even the another residual at the end. So the compute formula shown is, y is equals to, so we can, I would go literally over here, is equals to y is equals to x plus attention layer norm, and then z is equals to y plus, feed forward plus, layer norm. So each layer norm has separates gamma and beta parameters. These are tunable parameters, and these parameters repeat in GPT-3, which has 96 layers or more, or I think it's called 192. It basically, as the layer scale, layer norm operations, would be the double of the number of layers in some shape or form. So you can think of, if you have layers of 100, then layer norm's operation would be 200, because there's 2 in 1 layer. So layer norm ensures every layer receives input with mean equals 0. So if you have a raw activation with no normalization, we're now trying to basically make the input stable around 0 in some shape or form. And the variance is equals to 1. So it will not go more than 1. And then learn perfect adjustments. These charts show the dramatic difference. Raw activations are chaotic when shifting mean. Now 2.3 and growing variance causing training and stability. With layer norm, we get stable mean and variance enabling consistent training. The mathematical forcing of stable distribution is what makes deep neural networks trainable. So this is not just random algorithm into a neural network. It's a lot of it has got to do with stabilizing the back propagation so that you can get a much more stable neural network. And that's the importance of LayerNorm. Even though the math seems simple, the question is, why do we have it? It's mostly because we want to stabilize the training. And here, this is the formula output. We'll go more into the formula and the math behind it, but this is what the purpose of why we're doing it is, why, is what I'm trying to explain over here. So let's look at what we're actually activating and what we're training. So when we look at an image like this, there are certain things that you can train, which is, the brightness, the color, the contrast. And as I change this, you can see how the final input changes. And these are all trainable parameters of basically a layer norm. You can train the scaling, you can train the shifting. So you might say, I want to have a certain flavor to my thing. And this is all trainable based on the inputs and outputs of your neural network. And that's what really is happening. So if you could have a very different type of canvas, you're trying to basically adjust, to a certain format in such a way that it automatically, it stabilizes across a specific, brightness, color tint, and contrast. So LayerNorm first creates, a neutral canvas, which means 0 and variance 1, then learns the perfect, gamma, which is known as scaling, and beta, which is known as shifting for each layer. And that's what these sliders show, the control of what we're actually training, from an image standpoint, just to get an intuitive feel of, what we're trying to do with the math. And then here you have features, more pronounced, like lower gamma, would compresses them. Beta controls the center point. It shifts the entire distribution. The network learns these parameters during training to find the optimal statistical, properties for each layer specific function. Let's go to the formula. So the formula at the high level is the entire operation, captured by this equation. One thing I love about neural networks at this point in time, that everything about neural networks has actually been invented, 400 years ago in some shape or form. The algebra, the math, the calculus, everything is, just basic mathematics that anyone could literally, Google this and find in Wikipedia, and the math will explain to you itself. That's one thing that I love about this, is that even though we're living in 2025 and a lot of cool things are happening at the highest level, the fundamentals is just, just basic stuff. And all we're going to do is dive and dive deep into this math over here. So the first thing in that equation is, you'll notice, is that we need to first find the mean. And the mean is basically taking the x. X will be, say for example, you have a token, and we'll go to the code as well. Say you have an input, say the word the would have a dense representation, which would be the embedding dimension. So what we're trying to do is we're taking and summing all that embedding dimension for that one token, and then we'll find the mean of that token. And that's what the mean does, is basically the average. And then we create the variance. The variance is taking that x minus the mean, the whole square, and then you divide it by the number of features. So for each feature, we find the difference between its value and the mean. We square that differences so that the result is positive, and it penalizes large deviations. And we sum all them up, square the differences, and then we average them up, which is the variance. It's basically a normal distribution in that sense. And then we normalize it. We center the data around 0, which is x minus mu. And then this is the standard deviation, or the reciprocal standard deviation, as they call it, RSD. And then we put an epsilon over here. And it's added for numerical stability to prevent divisions by 0 if the variance is 0. And the result is that this x is the new vector where the features have a mean of 0 and a variance of 1. And this is just the normalization step. And then we do the, the scaling and shifting. And here we do the dimensions. Then finally, we scale and shift the normalized vector using learned parameters. Here, the dimensions of each tensors are for a single token. And one thing that you need to know, especially in neural networks, I think if you understand a few concepts, it's much easier to understand that it's not very complex in that sense, because there are few things that really matter. One is to understand the matrix dimensions. So the input x has got a dimension of c, which is your embedding, which is 1D for a token, but c is basically the dimension of your embeddings. Mean is just one scalar floating point. Variance is just one number. And again, gamma is the same dimension as embeddings. Beta is the same dimension of embeddings. Output is also the same dimension of embeddings. So you're basically multiplying your x, which we just got from earlier, the normalized input. And then we're multiplying it by gamma. And then from gamma, we are then adding beta. And that's the output. That's normalization. And that's LayerNorm. So you're basically scaling and shifting. So the gamma part will scale the parameters and the beta part will shift the parameters, similar to what we did in our, in that image that we showed earlier. And what LayerNorm actually did was that where do you position LayerNorm also is very important. You can't just position a LayerNorm anywhere. So in BERT, this is the original transformer paper, came in 2017. And in 2018, BERT came, which was a 12 to 24 layer, and then GPT-2 came, which was around 48 layers or so. And the story of the two lines of code that I want to just show over here is that BERT uses post-LayerNorm, which is after adding the residual connection. And in 2019, GPT-2 makes the breakthrough. It says that normalization should be before the function call. And the timeline shows the progression. BERT pioneered transformers, but was limited by the post-LayerNorm architecture. And then GPT-2 came, and then it basically said that LayerNorm should be at the pre and not at the post. And this allowed for it to be much more stable in basically having much more layers, because you want to have a stabilized training, as we talked about a little bit earlier. And this is the major difference in not just understanding why LayerNorm is important, but where do you position it. So in the BERT style, which I still use BERT for a lot of embeddings and generating embeddings, but it's limited by how many layers it can have. Beyond that, it will not really be a great model. You'll have to use a different model. At least you need to switch LayerNorm. So what happens is that once you have BERT style post LayerNorm, which I showed you earlier, so you'll have a function, and then you have LayerNorm, and then you have an output. The training symptoms is that the residual connection X gets added before normalization. And looking at this diagram, the residual path goes through LayerNorm, creating gradients flow issues. The problem, gradient must flow through the normalization operation. The residual path isn't clean, making it harder to train very deep networks. BERT was limited to around 24 layers because of this architectural choice. And then GPT-2's breakthrough, y is equals to x plus f LayerNorm x, happens before the function. So now here we put LayerNorm before the function, and keeping the residual path completely clean. So now we have the residual path that goes beautifully in. And that clean path we indicated. The residual connection X stays untouched, providing a clean gradient highway. Benefits: clear gradient flow through residual, much more stable training, and can train very deep networks, which is now around 96 plus layers. And it enabled GPT-3, GPT-4, GPT-5, and what we have today, which is what makes model LLMs work. So BERT basically kind of like was limited by the layers, and then GPT-2 and OpenAI came up and said let's put LayerNorm before for a more stable gradient connection, so that we can increase our layers, and then we have more stable training. And this was one of the biggest improvements, and all they really did was kind of like move the LayerNorm from one location to the other. So the gradient flow tells us the whole story. Now post LayerNorm, this is what would happen. So you have multiple layers, and here you have post LayerNorm. So the pre-LayerNorm when you start the layer, and when you have post. And let's look at what happens once you start to do the backward propagation. It starts to go to bigger, 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 and bigger, and this is what it explodes to a point where it's very unstable at bigger depths. All right, and this mathematical difference is why modern transformers can train with hundreds of layers, while BERT was limited to 24. And this is really what happened. The architectural revolution was literally moving 2 lines of code. And this was Google and this was OpenAI. And at least, all the other details, keeping things, in context. But this was one of the biggest, breakthroughs of how important LayerNorm's positioning was. And the birth style LayerNorm X+ attention, and then you put, LayerNorm over here, and then you go to the output. In GPT-2, they basically said that before the function normalizes, let's put LayerNorm over here. And then we give out the output for the layer as X+ output. And the entire modern LLM era started from just this particular change. And sometimes the most profound advances come from the simplest architectural change. So let's look at how we are now organizing this from an HPC standpoint. And because this is also important, because what we do over here, at least in this particular video series, is not just taking an AI and making the AI from the ground up. It's also applying HPC concepts, on CPUs and figuring out the memory layout and doing it in C. So let's have a look at what that might look like. So here is the memory layout, which we'll be going through in the C code. It's all there in the GitHub repository. I'll also put them down in the description below. And one thing that I've done is try to put everything very contiguous in one memory. Everything needs to be beautifully aligned, from the embeddings to the tokens to the weights and all that cool stuff. So here I have LayerNorm 1, which is the offset, which we have the gamma, and then we have the beta weights, and then here we have the outputs of the mean offset and the residual reciprocal standard deviation, and then the outputs of the LayerNorm for all the tokens. So if you look at the code, what will happen is when you look at a CPU in some shape or form, you have the memory, which is in DRAM, and then you have the CPU of how it works. So what really happens? So the first thing is that you take this data. So we're really focusing on how do we take this to make this very efficient with, when you're dealing with all of this computation. So it's not just about understanding the mathematical concepts, but how does it actually work in a CPU? So we take this data and it goes through the shared L3 cache, which is common to all the cores. And then, which is basically the first step in some shape or form, right? Is to take all the data, which is the gamma and beta to L3, including the input. And then for that particular token, it goes to L2 cache, and then it goes to L1 cache, and then we use AVX-512, or you can use AMX. And then we're going out there and doing the summing vector, we're doing the addition, and doing all the, the mean, the reciprocal standard deviation, and we're doing all that cool stuff. And then we're doing the shifting and scaling, and then we're storing it into the output of the offset. And this is happening per token, per token, per token, per token. And the beauty about all of this is that we're trying to minimize cache misses. We're trying to, make sure that there's a lot of cache hits, minimize TLB misses, and making sure everything runs very smoothly because this is running at very high speeds, and it can do a lot of computation very, very quickly, provided everything is done in a very smooth manner. Because if there's one memory misalignment here, memory misalignment over here, well, wasting clock cycles. Because each time they were fetching from DRAM, we're having a lot of issues. Issues in the sense that, you could waste clock cycles. So a lot of my code in this particular series is to show that yes, one is the mathematical formula, and this is how the AI works, but a lot of it is also how do you implement it in such a way that it can, commodity hardware can run all of this. And this is a very critical part of my research in some shape or form. And let's look at the code of what how we kind of like make all of this work in some shape or form. So here it's pretty much a very straightforward function, and I'll be very honest, even though it looks a little bit complex with all the single instruction multiple data, where I'm using the AVX-512 for loading the packed single precision, it's all basically the first thing is compute the mean. Compute the mean, you're just adding all of them, you're going to the model dimensions for that one specific token, you're going through all the mean, and then you're basically packing around 16 bytes of data, which is float 32. You keep adding them, you load it into the vector, into the M512, AVX-512 variable, and then you keep adding and adding and adding. And in case if it's not cache aligned, then you do some scalar adding. And once you add everything, you basically reduce all of it, and then you create the mean. The mean is basically divided by the number of D model, the size of your D model. And once you have that mean, it's pretty straightforward code. And the next part is doing the variance, and the variance is going to be that mean minus your input, that the feature of that input, the whole square. So in the variance, I've done a few little tricky things. So we're just going to go through a little bit of the details. We're doing the same thing. We're going to subtract from that mean, and then we do a fused multiply and add. So we're doing the whole square, and then we're adding the variance to the vector. So we're taking the multiply and add to get the variance, and then what we need to do is we're going to create the 1 divided by the square root of RSD plus epsilon. So what we're doing is we are taking the variance, we're dividing it by the model, we're adding in that EPS, which is the we really don't want us to divide by 0. So what if the model is 0? We don't want everything to be 0. So we're having like this very, very small number, like 0.001, just in case that we have some precision. And here what we do is we cast it to a double. And the reason why we cast it to a double is because when we do a square root, we can get a very, a high precision number. So when we do it in double, we can get that high precision number, and then we can cast it back to float so that we have a much higher precision, which is casted to float to get that that inverse standard deviation. And then once we have that inverse standard deviation, we then basically set it, and then we store the mean and the inverse standard deviation. So this is just a lot of AVX-512 advanced code, but in reality we're just following the formula, x minus mu the whole square divided by 1 divided by square root of plus epsilon. And it's really in this many lines of code you're creating the variance. And then the last part is to calculate the whole gamma and beta, where you multiply it by gamma, and you add and then you add the beta. And because it's scalar, you can do this all in one loop pretty straightforwardly. And you're using the MMX AVX-512 to do all of the 16 bytes at once. And even if it's not cache aligned, if your D model is not cache aligned, then at the end you just kind of like do the scalar operations over here. That's really it. The code is very straightforward. You create the mean, you create the inverse standard deviation, and then you do the scaling and the the shifting. And that's the XIMD instructions. And we'll go to the code shortly right now. So yeah, let's go to the code. So this is the C code that I have over here. So what we've done over here is, if you look, I basically have a couple of LayerNorm kind of like functions. I have the naive serial. The naive serial is basically doing it without any MMX or AVX-512 single instruction multiple data. It's very simple. You calculate the mean. It's very straightforward to read. You calculate the variance, and then you scale and shift. Beautiful, super clean, not very efficient. And then here we do with the forward roll slice. And here is what I just explained to you on how we can, kind of like use the single instruction multiple data, which is the AVX-512, to kind of like, speed that up by processing 16 bytes of data at once and being a little bit smart about our CPU's capabilities and accelerators. That's really it. And the function calling this, the LayerNorm forward roll slice, I also have for an unroll slice. This is a much more advanced technique when you do not have hyperthreading, so that you can unroll a lot more of the for loop. But the function that's calling this, the roll slice, is now doing the parallelization, which is saying that for every token, we pass it to that one core, that one core do the LayerNorm. So each core is now only processing that one specific token, and it's continuing to do this, in a very sequential manner. So that's really what's really happening in this whole, process over here. Now here we do have a small little for loop, so that because what we're doing over here is we're passing it a bunch of few tokens for the specific core, so that it can kind of like crunch these numbers very quickly instead of constantly being called by the parent function, just for a little bit of speed in some shape or form. And yeah, and that's really it. And then when I kind of like ran this whole thing on this particular CPU, just kind of like going back, what I have over here is like just kind of like testing the speeds between the naive implementation and the non-naive implementation, especially for the LayerNorm thing. So if I use the LayerNorm G-flops, I'm getting around 7.75. But then once I start to do the kind of like the more optimized version of using the token parallelization and with single instruction multiple data, you can get around like 3-4 times the speed up. I think from a speed up standpoint, this can be really improved, and it can be really helpful. So that's the kind of like speed up that you can do with high performance compute. There's still a lot of certain things that I would kind of like tweak over here with this particular hardware. I would want to minimize hyperthreading, and so that you can have less cache misses and more cache hits and kind of things. But I don't have control over this BIOS, so the least I can do is at least optimize the algorithm itself using the sum of the accelerators. So LayerNorm represents a perfect example of how deep understanding across multiple layers creates transformative technology. The mathematical insights, understanding internal, the covariance shift led to the normalization formula that stabilizes training. And then the architectural innovation, the LayerNorm by two lines enable deep networks, unlock the modern era. And the implementation mastery, which is really important, is that if you do a single instruction multiple data optimization, it achieves near hardware limit performance through careful memory management and vectorization. And this is the kind of full stack thinking, right, from the mathematical foundations to hardware optimization that drives the real AI progress. And if you have any questions below, please do ask before, down in the comments before, because the whole idea is that if you didn't have LayerNorm, you would not have ChatGPT and all the modern AI, because that training stabilization is a huge part. If your training is not going to be able to train your AI, good luck, right? So that's the full journey of LayerNorm. We saw how it began as a clever mathematical solution to the problem of internal covariance shifts, which then creates this chaos during training. And we then witnessed the architectural revolution, which is sparked by the shift to pre-LayerNorm for the layer in models like GPT-2, a change that stabilized gradients and enabled the creation of the truly deep neural networks that we have today. And finally, we brought that back to our own LLM runtime, the implementation, the excellence discussed using single instruction multiple data to optimize the kernel is precisely the approach we're taking in our source code to make these operations kind of like fly on the CPU. And the functions like LayerNorm forward roll slice and LayerNorm token parallel in our projects are the direct practical applications of these high performance computing principles. So in the next video, we'll take the kernel we've optimized for both LayerNorm and GEMM and stitch them together to execute a full forward pass. We'll actually focus on the attention mechanism, and then we focus on the multi-layer perceptron, and then we'll wire all of this up together, to create, pretty much the whole GPT-2, and we'll create the residual connection, benchmark the entire process from end to end. So thanks for joining me on this deep dive. If you're enjoying these series where we go from theory to high performance code, be sure to like and subscribe the video. The source code is always linked in the description below, and see you in the next one.